All right, probability review part 2, distribution of means or distribution of X bar or distribution of the averages. In other words, this is central limit theorem, probably the most important thing in all of statistics. Look for the word normally distributed and the phrases sampling distribution of X bar. All right, so if you're say sampling distribution of X bar, sampling distribution of the means, or sampling distribution of the average, you're going to be using this formula or perhaps a T formula, depending on whether or not the standard deviation of the sample is used or the standard deviation of the population. But for today, we're going to focus on the Z, all right? So to be normal by central limit theorem, either the underlying population must be normal or the sample size must be 30 or greater, all right? So if it's, regardless what happens, if we have a sample size greater than 1, and they're asking for the distributions of means, it doesn't have to be 30 or larger. This will be the standard deviation, but it doesn't become normal until the sample size is 30 or larger. So example, the scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. What's probably a group of 7 randomly adults have an IQ below 95. So my picture looks something like this. We have a mean of 100, and we have an X of 95. And we were looking for the probability that X is less than 95. And we are going to go ahead and write our formula. Z equals X bar minus mean, standard deviation of 15 divided by the square root of 7. This is standard deviation and this is n. So we're going to look for the probability that Z is less than 95 minus 100 over 15 divided by the square root of 7. You're like, well, wait a second, Mr. Spencer. We can't do that because our sample size is less than 30. And you would be right, except for the fact that they already told us it was normal. If it's normal, you're good to go with any sample size. So we're good to go with this. Now, there's a couple ways to go about this. I'm going to use the norm CDF. And they ask for the probability. So a norm CDF works. So second vars, norm CDF. And lower bound is negative infinity. Upper bound, 95. Mean of 100. Now here's where you have to be careful. Our standard deviation is 15 divided by the square root of 7. And I just raise it to the half power like that. And we end up getting 0.1889. Now, there's another way about this that you may like, prefers, that test. And I could do a z-test. And my mean would be 100. My standard deviation is 15. My X bar is 95. My n happens to be 7. And they wanted a less than, because that's the way I shaded. Oops. Went too fast. And I still get the 0.1889. All right. So either way, that'll work. The next thing, which of the following is true about central limit theorem? So no matter how the population is distributed, as the sample size increases, the mean of the sample becomes close to the mean of the population. No, the mean of the sample already equals the population. We claim X bar equals mu. So it doesn't matter sample size. We don't care. It doesn't have to do with this increase. The word problem is here, and it becomes close. It doesn't become close, it is, all right? So X bar equals mu regardless of the sample size. Part B, no matter how the population is distributed, as the sample size increases, the standard deviation of the sample becomes closer to the standard deviation of the population divided by the square root of the sample size. All right, so I'm going to reread that. No matter how the population is distributed, as the sample size increases, the standard deviation of the sample means becomes closer to the standard deviation of the population divided by the square root of the sample size. No, it doesn't become closer. Regardless of the underlying distribution and regardless of the sample size, the standard deviation of the X bars does equal the standard deviation of the population divided by the square root of n. It doesn't become closer, it just plain equals it regardless of the sample size. All right, if the population is normally distributed, then as the sample size increases, the sampling distribution of the sample means becomes closer to the normal. If the population, no, if the population is normally distributed, guess what? The sampling distribution of the sample means equals a normal. All right, it doesn't become closer. The sampling distribution of sample means is normal. All right, if the population is normally distributed, then the sampling distribution of the sample means is normal, regardless of sample size. So this is wrong. So central limit theorem refers to something else, and yes, it does. Central limit theorem says if we have, regardless of the underlying shape, all right, if it's not normal, if you increase the sample size, it becomes normal for n greater than or equal to 30, right? So the distribution of the sample means becomes, for any population non-normal, becomes normal for n greater than or equal to 30, or approximates the normal, gets close to it. So n greater than or equal to 30, a skewed distribution approximates the normal, the distribution of the means, not the sample, the distribution of the means. That's very important that we talk about the distribution of the sampling means or the distribution of the X bars. So there were 5,317 owned homes in a Western city in the year 2000. The distribution of sales price of these homes was strongly skewed to the right, which means it was stretched out to the right. It was pulled that way, pulled to the right, with a mean of 206,000 and a standard deviation of 37,881. If all possible samples of size 100 are drawn and the mean is computed for each of these samples, describe the sampling distribution. Well, the nice thing is the mean is describe the distribution of the sample. This is key. The mean is always going to be whatever the mean is. So the mean is 206,274. All right, the standard deviation. Well, guess what? They said distribution of the sample, not distribution of the sample means. All right, not the distribution of the sample X bars, not the sampling distribution of the X bars, not the sampling. So because of that, the standard deviation of the samples is going to be this, and the shape skewed right. It didn't change. The distribution of the sample will always follow the distribution. If it had been normal, it would have been normal, but whatever the shape is, it'll be that. Now it says describe the distribution of the sampling means. Well, once again, the mean is 206,274. Well, that was nice. The standard deviation is now going to be 37,881 divided by the square root of 100. All right, what's the big difference here? Sampling means, sampling X bar, the distribution of these sampling averages, something that indicates mean, average, or X bar needs to be here. And now the shape is approximately normal. Because n is greater than 30. all right? Because n equals 100 or is greater than 30, it approximates the normal. So let X be a random variable that is skewed distribution with a mean of 10 and a standard deviation of 10. Based on the random sample, describe the sampling distribution of X bar. That's the key word. All right, so first off, nice thing. The mean, and the appropriate way is the mean of X bar equals 10. Standard deviation of X bar is going to equal 10 divided by the square root of 400, which is 10 over 20, which is 0.5. And the shape is approximately normal by CLT. Don't abbreviate, but I'm going to shorten the video, by central limit theorem. All right, because our sample size n equals 400, which is greater than or equal to 30. Shape is normal, approximately normal by central limit theorem. Suppose the average outstanding loan for college is 23,500 with a standard deviation of 7,200 and a simple random sample of 50 college graduates. What's the probability their mean outstanding loan is under 21,000? So here's what we have. 23,500, 21,000, and I know I'm going to be using z equals x bar minus mu sigma divided by the square root of n, and you're like, how do you know that? Because I have a sample size 50. If it's a sample of 1, I couldn't do this. And I want the probability that x bar is less than 21,000, which is going to be the probability that z is less than 21,000 minus 23,500 over, where's my standard deviation? 7,200 divided by the square root of 50. So 2 ways to do this. I'm going to do this norm CDF, second bars, normal CDF, lower bound, we went to negative infinity, upper bound, 21,000, mean 23,500, standard deviation, 7,000 divided by 50 raised to the half power. And I get 0.00577. For those of you who want to do this as a stat test, z-test, mean 23,500, standard deviation 7,000, x bar is 21,000, sample size 50, we wanted less than. Somehow I know that I did something wrong. Oh, 21, 1, 2, 3. There we go. 0.00577. A new soft drink has an average number of 77 calories per bottle with a standard deviation of 4.5. In a random sample of 40, what's the probability that the mean number of calories is between 75 and 80? Okay, so once again, we're looking for the mean. So that tells me I'm looking for z equals x bar minus mu sigma divided by the square root of n. All right. Now here, when I read this thing, they didn't tell me it was normal. But because of my sample size being 40 is, my sample size 40 is greater than 30, I can use the normal distribution. All right. Even though they didn't tell me, I can still do it. And so the mean is 77. The mean always stays the mean. And we want between 75 and 80. So this is what I'm looking for. All right. So this is the probability that 75 is less than X bar is less than, and by the way, make sure it's an X bar, is less than 80. So this is a probability that Z is less than 80 minus 77 over 4.5 divided by square root of 40 minus the probability that Z is less than 75 minus 77, 4.5 divided by square root of 40. This is work shown. Let's show that. And second bars, normal CDF, lower bound, looking at my picture, 75, upper bound, 80, mean, 77, standard deviation, 4.5 divided by 40 raised to the half power. And almost all, 99.7%, lie within that interval. Finally, consider the sampling distribution of a sample mean obtained by a random sample from an infinite population. The population has a distribution that is highly skewed towards the large values. When they say that, that means it is skewed to the right. It's been stretched to high values. How is the mean of the sampling distribution related to the mean of the population? All right, so I'm just going to answer that question as opposed to write it down. The mean of the sampling distribution equals the mean of the population regardless, always. Doesn't matter sample size, etc. The mean of the sampling distribution equals the mean of the population, right? How is the standard deviation of the sampling distribution related to the standard deviation of the population? So this is part B. So I guess I should, part B, the standard deviation of the standard deviation of the sampling distribution of X bar equals the standard deviation of the population divided by the square root of n. So basically, and you would need not just to put it in symbols, you'd have to say that. You'd have to say the standard deviation of the sampling distribution equals the standard deviation of the population divided by the square root of n. And that is regardless of sample size. N does not have to be 30, all right? N does not have to be 30. This is always true. Always true. And by the way, I guess I should say that for A. The mean of X bar equals the mean of the population. That's always true. That's always true as well. And again, you can't just do it with symbols. You're going to have to say it out in words. So you're going to have to say the mean of the sampling distribution, the mean of X bar, equals the mean of the population, regardless of sample size. It's always true. The standard deviation of the sampling distribution equals the standard deviation of the population divided by the square root of the sample size. And that's always true. All right. And that's always true. Okay. Now, finally, how is the shape of the sampling distribution affected by the sample size? All right. So we have two things to do. We need to address n less than 30 and n greater than 30. Greater than or equal to 30. As n increases, the distribution shape is approximately normal for sample sizes greater than 30. The distribution of the sample is not normal for sample sizes less than 30. Matter of fact, it contains some of the skewed properties, but you need to address both things. They didn't say what the sample size was. So the distribution shape the sample is not normal for sample sizes less than 30. And then the distribution of the sample X bars is not normal. Distribution, as it increases the distribution shape of X bars is approximately normal. And make sure you talk about the means. All right, it's the distribution of the sample means is approximately normal for sample sizes greater than 30. All right, that concludes this. Thank you.